Welcome back to the course on plasma physics and applications. In the last module, we have learned that at the core of the generation of magnetic fields in the Sun is a dynamo process which converts energy of the plasma flow into energy of the magnetic field. Magnetic flux ropes with large magnetic fields form and emerge from the interior through the photosphere. In the course of this lecture, I will first describe how magnetic buoyancy can result in the emergence of the flux rope, and I will then detail how magnetic fields of different flux ropes can interact. You will discover that magnetic field lines can break, reconnect, change the topology of the fields by converting a large fraction of the magnetic energy into energy of the plasma flow. This process is called magnetic reconnection and is at the core of the most spectacular event in the Sun, the coronal mass ejection. To describe it in quantitative way, we will derive the Sweet-Parker model, which is based on the equation of the resistive MHD that you have learned in previous modules. We have seen that modeling of the solar dynamo requires the emergence of bundles of magnetic field, called flux tubes or flux ropes, from the interior of the Sun through the surface. The existence of flux ropes have been theorized since the early 70s. But have these flux tubes been observed in reality? The answer is yes. This movie was taken on July the 18th, 2012, from the Atmospheric Imaging Assembly and showed the Sun activity in the extreme ultraviolet. This movie showed for the first time the formation of a flux rope. On that day, a burst of light, called a flare, was caught from the Sun by the Solar Dynamic Observatory. These flares are very often associated with the eruption of solar material, known as coronal mass ejection or CME, but this one was not. Instead, the magnetic field lines in this area of the Sun's corona started to twist and kink, and the plasma started emitting very strongly in extreme ultraviolet. The formation of the flux ropes and their twisting and kinking are clearly visible in red color in this movie. 8 hours later, on July the 19th, the same region of the Sun flared again. This time the flux rope connection to the Sun was cut, and magnetic field escaped into space, dragging billions of tons of solar material, and this was a classic CME. To allow this process, magnetic reconnection must be at play. Before dealing with magnetic reconnection, let's see how a flux rope can emerge from the interior. What can make the flux tube emerge? The answer is magnetic buoyancy, which is similar in physics to an emerging submarine. Consider a flux tube which is immersed in the solar plasma underneath the surface, and it is perpendicularly oriented to the solar gravity. Plasma in the flux tube has a pressure P, and that the plasma outside the flux tube has a pressure P external. This flux tube has a magnetic field B, which is much larger than the magnetic field characterizing the outside environment. Let's now consider a cylindrical coordinate system centered in the center of the flux tube, and let's write down the MHD equilibrium in the radial direction. In this equation, the sum of the plasma pressure plus the magnetic energy inside the tube must balance the external pressure plus the magnetic energy outside the tube. However, this last can be neglected since the magnetic field outside the flux tube is much smaller than the magnetic field inside the tube. Let's now make the isothermal approximation, and let's assume that the temperature inside and outside the flux tube is not too different. If we now assume that the flux tube is characterized by a plasma density ρ, and the plasma outside the flux tube is characterized by a plasma density ρ external, and we use the equation of state for ideal gas, we can write the following. From this equation we obtain that, which tells us that the flux tube is less dense than the surrounding plasma. Therefore, the flux tube will experience a buoyancy force which can be expressed as the difference between the two density times the volume of the flux tube times the gravitational acceleration. Just as for a submarine floating, the flux tube will be therefore subject to a buoyancy force which will tend to push the flux tube upwards towards the surface of the Sun. Once flux ropes have emerged from the interior through the surface, how will they interact and how their magnetic fields will evolve? The image on the left shows a series of magnetic loops from the previous movie. The image on the right has been processed to highlight the edges of each flux loop and make the structure more clear. Now, for the sake of the discussion, let's suppose that the magnetic fields are oriented like this in these flux ropes. We can observe that a complex 3D magnetic field can develop in which opposite directing magnetic fields are brought together by plasma flows. For example, let's suppose that in this flux rope the magnetic field is oriented in the following way, and the plasma flow with the velocity v is squeezing the flux rope. In a second time, we can observe that a complex 3D magnetic field can develop in which opposite directly magnetic fields are brought together by the plasma flow and they start to interact in a small region. In the following, we will see that magnetic reconnection is at the basis of the interaction of opposite directed field lines. To describe the interactions of magnetic fields, let's go back to the resistive MHD equations that you have seen in previous modules. The key parameter in this equation is the magnetic Reynolds number, which in most astrophysical systems is much larger than 1. Let's suppose that we start from a situation where we have opposite directed magnetic field lines, as shown in this picture, which are embedded in a plasma with a magnetic Reynolds number much larger than 1. Now, we push the magnetic field lines one against the other by inducing a plasma flow with the velocity v. Which are the consequences of a large magnetic Reynolds number? The advection dominates the plasma dynamics. Therefore, the magnetic field lines are frozen to the plasma and the ideal MHD holds. This means that the magnetic diffusivity term can be neglected. Another important consequence of a magnetic Reynolds number very large is that the magnetic flux is frozen to the plasma motion, and therefore the magnetic field lines cannot break or reconnect. This means that no change in the magnetic topology are allowed. If we keep pushing the magnetic field lines with the velocity v, then we get closer and closer, and the magnetic flux will be compressing between them. This in turn will increase the magnetic field gradients, which are characterized by the spatial distance d, and as a consequence the magnetic Reynolds number will be decreased in a small layer across the opposite directed magnetic field lines. Therefore, very thin regions can form where the gradients of the magnetic fields are very large. In this thin region, a current developed in the perpendicular plane, and the ideal MHD does not hold anymore. In this very thin region where the ideal MHD is violated, magnetic reconnection can happen. A magnetic field line which is pushed by the plasma flow against a magnetic field line which is opposite directed will break and reconnect, thus forming a new magnetic field line. Which are the consequences of magnetic reconnection? As you can see, the global topology of the magnetic field now has changed, and these affect the path of particle and heat conduction. As we will see in the following slides, the magnetic energy is converted into heat, kinetic energy, and fast particle energy. During magnetic reconnection, large electric currents and fields are generated at the reconnection sites, as well as shocks, waves, and filamentation. Let's now describe the magnetic reconnection dynamic using a simple model, the Sweet-Parker model, that was originally proposed by Sweet in 1958 and by Parker in 1957. This was the first quantitative model of magnetic reconnection to be developed. The geometry of the Sweet-Parker model is represented here. Opposite directed field lines with a magnetic field intensity B0 are brought together by a plasma flow with a velocity V0. They form a current sheet of length 2L and thickness 2D, shown here in red. Reconnection happens in the current sheet, and the new magnetic field lines are now flowing out of the current sheet with a velocity V out and a magnetic field intensity B out. To derive the model, we make the following hypothesis. Outside the current sheet, the magnetic Reynolds number is much larger than 1. Inside the current sheet, the plasma has a resistivity indicated by eta. The system is in steady state, meaning that time derivatives can be neglected. The plasma is incompressible, and we assume a two-dimensional geometry with d over dy equal to 0. To derive the Sweet-Parker model, we will use the continuity equation, the Ohm's law, and the equation of motion. Let's start with the continuity equation. Divergence of ρ times v equal to 0, where ρ is the mass density of the plasma. From this equation, using the coordinate system we have chosen, it's easy to write where delta y is the thickness of the layer in the y direction, which drops out. We can therefore obtain an equation that links the outflow velocity v out to the inflow velocity v0 via the thickness and the length of the current sheet. Let's now write the Ohm's law and consider the y component. At the edge of the current sheet, the y component of the current density is equal to 0. Therefore, using the Ohm's law, we obtain in the center of the current sheet, the flow stagnates, and therefore Vz equal to 0. We can therefore write that Ey is equal to eta Jy, where eta is the resistivity of the plasma. Now, writing the Ampere's law in the current sheet, we can easily obtain. Now, if we put together this equation and this equation, we obtain that using these two equations, we can eliminate Ey and obtain. If we now go back to the expression we found using the continuity equation, and we use the expression for V0 that we have just found, we can easily obtain an expression that links the outflow velocity to the inflow velocity via the resistivity and the length of the current sheet. Now, if we know V out, we now know the inflow velocity V0 and the shape of the current sheet characterized by its thickness divided by its length. The question is, how do we determine the outflow velocity? We will use the equation of motion. Let's write down the MHD equation of motion for a steady-state plasma. Let's now consider the current sheet with the XYZ reference system centered in its center. Let's make the further hypothesis that the gradients of the pressures can be neglected, and let's first compute the Lorentz force that acts along the current sheet in the x direction as follows. The Lorentz force accelerates the plasma from rest to the speed velocity to the outflow velocity V out over a distance L, the length of the current sheet. So we can write using the previous expression, we can obtain now, using the conservation of the magnetic flux, we can obtain this simple expression, which allows to compute the outflow plasma velocity, and by recalling the definition of the Alfvén speed, we obtain this important result that the plasma is accelerated at the Alfvén speed by the reconnection process. If we now define the Lundquist number, which is an I-dimensional number, and we recall the formulas that we have derived so far, we have fully characterized the current sheet in the Sweet-Parker model. In particular, we obtain that the inflow velocity is equal to the Alfvén speed divided by the square root of the Lundquist number, and the current sheet geometry defined by the ratio small d over L scales like 1 over the square root of the Lundquist number. Now, since in astrophysical systems the Lundquist number is usually much larger than 1, this formula tells us that in the Sweet-Parker model the current sheet is very thin. And this formula tells us that the plasma is flowing into the current sheet with a velocity which is much smaller than the Alfvén speed. Let's now do some energetic considerations. In the Sweet-Parker model, the sheet is thin and elongated. The plasma outflows from the current sheet at the Alfvén velocity. We can also compute the magnetic field at the exit of the current sheet using the flux conservation. And we obtain that it is much smaller than the magnetic field at the entrance of the magnetic field, since it scales like 1 over the square root of the Lundquist number. Let's now recall that the flux of the electromagnetic energy is given by the Poynting flux. And let's compute the Poynting flux at the edge of the current sheet. We have obtained this expression by recalling that we can now use this expression to compute the ratio of the kinetic energy flux by the magnetic energy flux. Recalling that the inflow plasma velocity is much smaller than the Alfvén velocity, we can easily conclude that most of the inflow energy is of magnetic nature. And what about the outflowing magnetic energy? This can be easily estimated, and by recalling that the B out is much smaller than B naught and small d is much smaller than L, we obtain the result that the outflowing magnetic energy can be neglected. Let's now compute the ratio of the outflowing kinetic energy flux to the inflowing magnetic energy flux. We obtain the important result that during magnetic reconnection in the simple Sweet-Parker model, half of the incoming magnetic energy is converted into plasma kinetic energy. I will not demonstrate, but the other half is converted into heat by Joule dissipation. Therefore, the reconnection layers act as a source of hot and fast plasma. How fast is this process? The plasma enters the current sheet at the velocity v0. This is also the rate at which the magnetic flux enters the current sheet. In this region, the plasma slips from the magnetic fields and flow out at the Alfvén speed along the current sheet. No more plasma can enter and carry magnetic flux until the previous one is left. An important parameter to define how fast the reconnection is happening is the so-called reconnection rate. This is defined as the ratio of the incoming flow velocity to the outcoming flow velocity, and in the Sweet-Parker model it is equal to. This shows that in the Sweet-Parker model the reconnection rate scales like the inverse of the square of the Lundquist number. Since the Lundquist number is much larger than 1 for many astrophysical systems, the Sweet-Parker rate leads to reconnection time that are many orders of magnitude larger than those that are observed. If we want to accelerate the reconnection rate, and you increase V0 externally from the outside, for a fixed Lundquist number, the reconnection rate remains constant, and therefore the Alfvén velocity must increase to maintain the same ratio. This is obtained by increasing the Alfvén velocity by increasing the incoming magnetic field. Therefore, pushing the reconnection harder from the outside does not increase the reconnection rate in the Sweet-Parker model, but only compresses the magnetic field. Let's now apply the Sweet-Parker model to two examples of magnetic reconnection in nature. The first example is a coronal mass ejection. A picture of a CME is shown here, where a beautiful prominence eruption produced a CME on April 16, 2012. Typical timescales for CMEs are of the order of 100 seconds. Magnetic reconnection is believed to be responsible for CMEs. Let's try to estimate the reconnection time from the Sweet-Parker model using the following formula. If we plug typical number for a coronal mass ejection into this formula, we end up with a prediction of approximately 10 to the 7 seconds, which is much larger than typical timescales which are usually observed. Therefore, the Sweet-Parker reconnection model produces a dynamics which is far too slow to describe coronal mass ejections. As a second example of magnetic reconnection, let's consider the sawtooth instability in tokamaks, in which plasma energy and particles are periodically expelled from the center of the plasma towards the edge. This picture shows an example of a sawtooth in a TCV discharge using the central suffix ray emission, which is roughly proportional to the square of the electron density and the electron temperature as a function of time. The central suffix ray emissivity drops dramatically over a very fast time scale during the so-called sawtooth crash. The poloidal cross-section profile of the suffix ray before and after the sawtooth crash clearly displays the redistribution of energy associated with sawtooth. Sawtooth crashes happen on the TCV tokamak on timescales of the order of 10 to 50 microseconds. This is the time during which magnetic reconnection occurs. If we estimate the Sweet-Parker reconnection time using typical values for TCV plasmas, we obtain reconnection time of the order between 1 and 10 milliseconds, which is too large if compared with the experimental values. In the two cases of magnetic reconnection that we have seen, the Sweet-Parker rate is too slow. How can we go beyond Sweet-Parker? If we want to decrease the reconnection time, we can, for example, act on the sheath thickness by modifying the sheath geometry. One example is the Pecek model for magnetic reconnection. Or we could, for example, increase the resistivity by introducing, for example, turbulence, which may give rise to anomalous resistivity. Or we could introduce new physics into our model by going, for example, beyond single fluid MHD, or by introducing three-dimensional physics. All these ways are subject of intensive studies in the scientific community. However, a number of open questions remains for magnetic reconnection. Among the most important open questions are: what are the causes of the fast reconnection rate? How does reconnection start? And when it starts, how are particles accelerated and heated? what is the interplay between the small-scale physics that happens in the current sheet and the global dynamics of the plasma. And probably one of the most difficult questions is, how can we model three-dimensional magnetic reconnection? To advance our understanding in the future, we will need more observational data, numerical simulation, and laboratory experiments. As an example of numerical simulation, I show you here a movie which is obtained from one of the most advanced numerical simulation of magnetic reconnection from a fully kinetic model. The simulation employed 2 trillion particles with 8 billion cells and was performed on the Blue Water machine at the University of Illinois. The movie shows the volume rendering of the current density during the magnetic reconnection. The complexity of this process, well beyond the simple Sweet-Parker model, is revealed by the development of fully three-dimensional turbulence in the current sheet. Numerical simulations are important to shed light on reconnection physics, and they must be compared against experimental data. These are difficult, if not impossible, to obtain from distance observations using telescopes and satellites. An important role can be therefore played by laboratory experiments, which provide easy diagnostic access and control experimental conditions. A number of magnetic reconnection laboratory experiments has been developed in the past and is presently under development with different geometries from two-dimensional to fully three-dimensional, and also covering different plasma regimes from Sweet-Parker to two-fluid MHD and kinetic reconnection. These will provide an important test bed for reconnection theories and simulations. In this module, we have explored the dynamics of solar flux tubes. They are affected by the plasma flow, and their opposite magnetic fields reconnect, change the plasma topology, and dissipate a large amount of magnetic energy that goes into particle acceleration plasma heating. Although the basics of magnetic reconnection can be caught by the simple two-dimensional Sweet-Parker model, the predictions of the reconnection time are not in agreement with the experimental data, which show much faster dynamics, for example, in coronal mass ejections or sawtooth in tokamaks. In the future, advancing our understanding of magnetic reconnection will require the use of observational data, sophisticated numerical simulation, and experiments in well-controlled and diagnosed laboratory devices. In the next module, we will explore how the plasma dynamics in the Sun can shape the surrounding environment by generating the solar wind.